All right, let's go. Number 5. A rogue star passes through and unmakes everything. The Milky Way contains several hundred billion stars, all of them moving, all of them on orbits that carry them through the galactic disk at velocities of tens to hundreds of kilometers per second relative to their neighbors. The solar system is not fixed in the galaxy. It is drifting, and so is everything around it. Statistical models of stellar encounters show that a star passes within 1 light-year of the Sun, roughly once every 100,000 years. At that distance, the gravitational perturbation on the Oort cloud, the vast spherical shell of cometary bodies extending up to 100,000 AU from the Sun, is significant. Billions of comets are dislodged from stable orbits and sent on trajectories that carry them deep into the inner solar system over the following millions of years, producing an extended bombardment that dwarfs anything in the geological record. But the close passage scenarios are worse. A star passing within a few hundred AU of the Sun, a distance less than the distance to the inner Oort cloud, occurs on timescales of hundreds of millions of years. At that distance, the gravitational disruption is severe enough to destabilize the orbits of the outer planets. Neptune and Uranus are the most vulnerable, sitting at the outermost edges of the planetary disk where the Sun's gravitational hold is weakest. Simulations show that a sufficiently close stellar encounter can place Uranus or Neptune on crossing orbits with the inner solar system, triggering a cascade of gravitational interactions that destabilizes Jupiter, Saturn, and eventually the terrestrial planets in sequence. The encounter that causes this will not announce itself. No beacon, no signal, no planetary alarm. Just a star that has been drifting toward us for millions of years, arriving close enough to rearrange everything, and then continuing on its way through the galaxy, entirely indifferent to the system it just dismantled. Number 4. The Sun's death sentence is already written. In approximately 5 billion years, the Sun runs out of hydrogen in its core. This is not a prediction subject to revision. It is a straightforward consequence of how much hydrogen the Sun contains, how fast it is fusing it, and how long that process can continue. The Sun has been burning for approximately 4.6 billion years. It has roughly the same amount of time remaining. When the hydrogen in the core is exhausted, fusion stops. Without the outward radiation pressure that has counterbalanced gravity for 10 billion years, the core contracts under its own weight. The contraction heats the surrounding hydrogen shell, igniting shell fusion, and the energy output increases dramatically. The outer layers of the Sun expand. Over the following billion years, the Sun swells into a red giant, eventually reaching a radius estimated at between 100 and 200 times its current size, potentially extending beyond the current orbit of Earth. At its maximum expansion, the Sun's luminosity will be approximately 2,000 times its current value. Mercury and Venus will be engulfed and vaporized. Whether Earth itself is consumed depends on the uncertain interplay between the Sun's expansion and the mass loss it undergoes as it sheds its outer layers, which pushes the planetary orbits outward. Earth may survive engulfment, but only to face a surface temperature of several thousand degrees Celsius, an ocean that boiled away over 1 billion years before the red giant phase even began, and an atmosphere stripped by the intensifying solar wind. What remains is a scorched, airless, molten rock orbiting a star in the process of dying. After the red giant phase, the Sun ejects its outer layers as a planetary nebula, and the core collapses into a white dwarf, roughly the size of Earth, cooling over trillions of years. The solar system does not end in an explosion. It ends in a long, slow dimming, and everything the Sun spent 10 billion years building is undone in the process. Number 3. A passing black hole eats the Sun from outside. The galaxy's invisible population is larger than you know. Stellar mass black holes, the collapsed remnants of massive stars, are estimated to number between 100 million and 1 billion in the Milky Way. They emit no light detectable at any practical distance. They carry no pulsar beacon.
They move on orbits perturbed by the supernova kicks they received at formation, which in many cases were large enough to send them on eccentric trajectories through the galactic disk at velocities of hundreds of kilometers per second. These objects are, for all practical purposes, invisible until they interact gravitationally with something nearby. A black hole of 10 solar masses drifting through the outer solar system at a typical galactic velocity would first reveal itself through anomalous perturbations of trans-Neptunian objects, subtle deviations in the orbits of Kuiper belt bodies that might be attributable to an undiscovered planet if the interloper was moving slowly enough. At velocities typical of unbound stellar remnants, the transit would be faster, the gravitational signature sharper, and the damage more acute. A black hole passing within a few AU of the Sun would gravitationally destabilize the inner solar system on a timescale of years to decades. The planet orbits, which are finely balanced gravitational arrangements that have persisted for 4 billion years, are exquisitely sensitive to external perturbation. Simulations of close black hole passages show that even a flyby at 10 AU, well outside the orbits of the inner planets, can nudge Jupiter's orbit enough to initiate a slow gravitational instability in the terrestrial planet system that unfolds over millions of years, eventually ejecting one or more planets into interstellar space. A closer passage within 1 or 2 AU could directly perturb Earth's orbit, altering its eccentricity and obliquity in ways that collapse the climate stability that has persisted since the Cambrian. The black hole would not stop. It would pass through, continue into the dark, and leave behind a solar system whose orbital architecture had been quietly broken. Number 2. The Sun evicts every planet one by one. The solar system is gravitationally unstable on long enough timescales, and the clock is already running. Numerical simulations of the long-term dynamical evolution of the solar system, including landmark work by Jacques Lascar in the 1990s and more recent N-body integrations spanning billions of years, consistently reveal that the inner solar system is chaotic. The orbits of Mercury, Venus, Earth, and Mars are not fixed periodic trajectories. They are quasi-periodic solutions of a chaotic dynamical system, sensitive to initial conditions in a way that makes precise long-term prediction impossible beyond approximately 100 million years. The most alarming result from these simulations concerns Mercury. In roughly 1% of long-term integration runs, Mercury's orbital eccentricity is pumped up by a secular resonance with Jupiter until its orbit crosses Venus's. A Mercury-Venus collision or a Mercury-Sun collision would send gravitational shock waves through the inner solar system. In a subset of these simulations, a Mercury destabilization cascades into a full inner solar system catastrophe within 100 million years. Earth's orbit is perturbed onto a collision course with Venus, or Earth is ejected entirely from the solar system. The probability of this outcome in the remaining lifetime of the Sun is roughly 1%. That is not a negligible number. 1% over 5 billion years means it is a real, physically plausible terminal scenario for this solar system, predicted by the same gravitational physics that explains every planetary orbit ever measured. The mechanism requires no external trigger, no rogue star, no black hole. Just the slow, mathematical accumulation of gravitational resonances between planets that have been nudging each other for 4 billion years, building toward an instability that the equations say is possible, and that nothing in the current configuration of the solar system can guarantee will not occur. Number 1. The Milky Way itself destroys the solar system. The collision has already been confirmed, and it is coming regardless. The Andromeda Galaxy, containing approximately 1 trillion stars, is moving toward the Milky Way at approximately 110 kilometers per second and will make first gravitational contact in roughly 4.5 billion years. The merger of the two galaxies will unfold across hundreds of millions of years. During the first passage, tidal forces strip enormous streams of stars from both galaxies, and the gravitational potential of the combined system fluctuates violently as the two galactic centers orbit each other before spiraling inward. For the solar system, embedded in one of the Milky Way's spiral arms, the danger is not direct stellar collision. The distances between individual stars are so vast that direct impacts during the merger are statistically improbable. The danger is the restructuring of the solar system's galactic orbit. As the two galactic potentials merge and the overall mass distribution of the combined system reorganizes, the orbit of the Sun through the galaxy changes. Simulations of the Milky Way-Andromeda merger show that a significant fraction of stars currently in the Milky Way disk end up on radically different orbits in the merged elliptical galaxy. Some migrating inward toward the dense galactic center, some ejected into the galactic halo, some thrown into the vast intergalactic space between the two galaxies entirely. The probability that the Sun is ejected from the merged galaxy entirely during the collision is estimated at roughly 3%. The probability that it is deposited on a dramatically different orbit, passing through denser stellar environments with higher encounter rates, elevated radiation backgrounds, and proximity to the merged supermassive black holes, is higher. If the solar system survives the red giant phase of the Sun, it will still face the Milky Way-Andromeda collision on approximately the same timescale. The merger will still be underway as the Sun enters its red giant phase. The two terminal processes overlap. The solar system ends not in one catastrophe, but in the convergence of several, each one inevitable, none of them negotiable, all of them already in motion.